Hello, AP Chemers. Today we're going to talk about calculating heat that is transferred when you have a phase change. So when your liquid turns into a solid or your liquid vaporizes or something like that. So we know that even when you are giving heat to a substance, the temperature does not change when you have a phase change. So, for example, let's draw the heating curve for water. Let's say this is for H2O. So, as I start at ice really cold, I heat it up, my temperature starts rising, but then when I reach 0 degrees Celsius, the temperature kind of remains steady. And then here I have melting happening. My solid turns into liquid, and then once it all turns into liquid, the temperature starts rising again as I'm giving it more heat. And then at 100 degrees Celsius, the temperature remains constant again. And what's happening here is vaporization. And then once it all turns into a gas, then it starts rising again. So we know that when we have phase changes like vaporization or melting or freezing or condensation, the temperature remains the same even though I'm giving it more heat. And so we had learned that Q is equal to MC delta T, but that only works if my temperature is increasing. So where I see an increase in temperature, and I'll mark it with green here. So there, and there, I can use Q equals MC delta T to solve for the amount of heat. But what if I'm here, where there are no changes in temperature? Then if I plug this in, I get delta T is equal to 0, which makes no sense. We know that it takes energy to melt ice or to vaporize water. And so we have this new equation, Q is equal to ml. So in Q equals ml, Q is the heat. It's measured in joules, like always. M is the mass, measured in grams. And L stands for latent heat. And latent heat is usually in joules per gram. Sometimes it's in joules per mole as well. If it was per mole, then you'd have to multiply by moles instead of grams. But the latent heat is basically the energy transferred for 1 gram of a substance to change state. Okay. Now we have latent heat of vaporization. We use that for evaporation or for condensation. We use the latent heat of vaporization, also known as delta H vap. For freezing and for melting, we use latent heat of fusion is what we call it. Fusion means melting. Delta H fuse. Now we use the same value for melting or freezing because it requires the same amount to melt a substance as it is released when it freezes. So it should be the same number, just one is positive, one is negative. So freezing we know is exothermic, so we'd use the negative value for latent heat of fusion. Melting would be endothermic, so we'd use the positive value. Same thing with evaporation and condensation. Evaporation is endo and condensation is exo. Okay, so on this diagram, let's have some handy numbers for water for you to use. So right here, I'm gonna go ahead and use this color here. This is where I would use delta H of vaporization. And for water, the delta H of vaporization, the latent heat of vaporization, is equal to 2,260 joules per gram. Now you don't need to memorize that number, it will be given to you on the test, but on the homework I might not give it to you, you just find it in your notes. Right here where you're melting, you'd use delta H of fusion, which is also known as the latent heat of fusion, same thing, 333 joules per gram. Okay, again, sometimes this might be given to you in joules per mole, so then instead of multiplying it by the mass, you multiply by the moles. So wherever you have this light blue, wherever you have a change in state, you're going to use Q equals ml. But whatever you have temperature change, you're going to use Q equals mc delta T. Now, one thing to look out for is when you're doing mc delta T, the C, if you remember from last year, is different for liquid water versus solid ice versus gaseous water vapor. So I'll write them down here so you have them for your notes. So C for water is 4.184 joules per gram Celsius. For gaseous water vapor, it is 2.03 joules per gram Celsius. And for ice, it is 2.06 joules per gram Celsius. While we're doing an energy or a heating curve, just a reminder, whenever you have a change in temperature, the change is in kinetic energy mostly. So your particles are moving faster when you increase their temperature. When you are doing a phase change, that energy that's released or absorbed is potential energy, changing your potential energy of your substance, the position of the particles. So when I melt, the position of the solid is different from the position of the liquid, or when my liquid vaporizes, the position of the liquid is very different from the position of the gas. So these are the numbers that we're going to use, and if on the exam, really, if they give you water or anything else, they will give you all these numbers to use. But for water, they know that you know that the freezing point is 0 Celsius, the boiling point is 100 Celsius. If they give you a different substance, let's say mercury, let's say acetone, hexane, any other liquid, and they give you problems to solve for it, they will give you these values, of course, just like they would with water, but they'll also have to give you what the freezing point of that substance is and the boiling point of that substance is as well, because you'll need those to be able to tell from where to where you do your different steps. But if you recall from last year, these are 5 different steps, right? And so on the homework or on the test, I could ask you to calculate the heat that is transferred, whether it's absorbed or released, in one little step, or 2 steps, or 3 steps, or 4 steps, or 5 steps. So let's practice one here. This one is 5, all 5 steps, just so you can see them. But you could be asked for just a part of this. So we want to determine the energy needed to bring 100 grams of ice at -7 Celsius, very cold, to 55 Celsius. I'm wrong, this was not 5 steps. This is just 3. So whenever you're given a heat calculation where you are changing phases, the key to this is to write out what steps you are using. So we are starting at -7 Celsius. So we are somewhere here. And I'm going to go ahead and mark it here. So I am somewhere here at -7. I'm going to go all the way to 55 Celsius. So somewhere right here. So I have 3 steps. This is my first step, this is my second step, and this is my third step. So I'm going to start with my first step. My first step is going from solid at -7 all the way up to solid at 0 Celsius. Oops. Okay, my second step, so this step right here, I'm going to go from the solid at 0 Celsius to liquid at 0 Celsius. And my last step, which is this one right here, I'm going to go from the liquid at 0 Celsius to the liquid at 55 Celsius. All right, so let's actually do our calculation. So the first step, you ask yourself, is this a phase change or a temperature change? Well, the phase is the same, they're both solids, but there is a temperature change, so that means I use Q equals MC delta T. So my mass is 100 grams. My C, this is ice, is 2.06 joules per gram Celsius. And my delta T is final minus initial, so 0 minus -7 is +7 Celsius. Okay, I'm going to add to that the next step. I'm doing a different color. Okay, my next step is this melting right here. So is it a temperature change or a phase change? Well, temperature didn't change, it's a phase change. So I'm going to use Q equals ml. So my mass is 100.00 grams. My latent heat of, and when I use fusion this time, is 333 joules per gram. Okay, my third step is this one right here, going from the liquid at 0 to the liquid at 55 Celsius. And so that is a temperature change. So I'm going to use Q equals MC delta T. So 100. My C is 4.184 because it's liquid water now. And my delta T is 55 minus 0, which is 55. And I add all of them together. So all together at the end, I think this one gives you 1,442 joules. This one gives you 33,300 joules, and this one gives you 23,012 joules. So all together, I got 58,000 joules, so 58 kilojoules. That's my answer. Sig figs for this are really hard to do, so I wouldn't worry about it too much. Just be reasonable with your sig figs. Remember, it's plus or minus 2 on the AP exam. All right, that's it for phase changes.